Right? Do I have that written down? We're going to talk about those gradients in a second. All right, so diffusion is when chemicals move down their gradient. For instance, high concentration to low concentration. Okay. And here's a little example. Let's say we've got our beaker and we put a cube of blue or purple, whatever that is, dye into the beaker. As it dissolves, we have this high concentration of purple right here at the bottom. And there is no purple at the rest of the beaker, so that's a large concentration gradient. The purple molecules, dye molecules, will diffuse from high concentration to the area of low concentration. So over time, the beaker gets more and more purple. This purple spreads out until the whole beaker is equally purple. And at that point, does molecular motion stop? No. So these purple molecules are still bouncing all over the place, but we don't have any more diffusion. There's no net diffusion. Because every time one of these purple molecules moves, let's say to the left, statistically there's one moving to the right to cancel it out. So there's no change in the purple distribution at this point, but individual molecules are still moving around. Everybody comfortable with that?
It's just not as drastic.
Well, in terms of the actual concentration, there's no measurable change in concentration, but individual molecules are still moving around. All right, so if we represented purples, if I came up to your chair, you'd come down here and you'd finish teaching the class. Should we try it? Okay. You're good. Maybe at the end of the semester. The group presentations? No? You guys are happy and excited about that. Okay. So let's talk about some characteristics of diffusion. Slide for that. Okay. So we're going to talk about simple diffusion now. And actually a lot of these characteristics are going to relate to diffusion in general. So I'll try to point that out as well. I guess I should mention why we're going to talk about simple. So what makes simple diffusion simple? In this case, going across a cell membrane. If the chemical can just squish right through a cell membrane, it can interact or get along with those phospholipid tails, then it can pass by simple diffusion. Okay? So it has to be able to get along with non-polar molecules. And it has to be relatively small. All right, so simple diffusion. And really diffusion in general is passive. Right, we talked about that before. All forms of diffusion are passive. We don't have to add energy to the system, but we now know where that energy comes from. It's the molecular motion. That's what's causing these things to move around. Also, with simple diffusion and diffusion in general, the larger the gradient, the faster diffusion occurs. The higher the rate of diffusion. So with that purple dye, right, you've got a lot of purple right there in the center, and there's no purple in the rest of the beaker a few slides ago. That's a large gradient. Diffusion's going to happen real fast. But towards the end, just before the whole beaker was equally purple, there was very little gradient. It was almost the same all the way around. So maybe some parts were a little less purple. Well, diffusion's going to be really slow there, right? Because it's less of a gradient. Right, so here we have this little box of water, and there's side 1 and side 2. We've got a bunch of purple spheres in side 1, none in 2. So it's a big gradient. Right? And so in the beginning, so compartment 1 has a high concentration of the purple spheres are glucose. A high concentration of glucose. Compartment 2 doesn't have any glucose at all, concentration of 0. Right? And so in the beginning, diffusion is going to occur very quickly. But as these two concentrations get closer and closer together, say at time B and eventually time C, then the rate of diffusion slows way down. They can still be bouncing around at the same speed, but the rate that they're spreading out throughout these compartments is a lot less. Okay? All right. So, what kind of gradient are we talking about? So as mentioned, concentration gradients, right? The number of molecules for a given volume. That's going to drive diffusion, but there's another gradient that can drive diffusion as well. And that would be electrical gradients. Electrical gradients. So if there's a difference in charge from one area to the other, the charged particle can diffuse right, towards its opposite charge. Let's look at an example. Okay. So here we're going to show chemical gradient. Let's imagine this circle represents a cell that has a high concentration of red inside the cell, relatively low concentration outside. That's a gradient. And so the red balls, the red circles, they're going to diffuse from high concentration in the cell to low concentration outside the cell. Also, the opposite could be true. If we had a high concentration of red outside, low concentration inside, diffusion would tend to go into the cell. Okay? That's all based on concentration gradients, right? The number of particles in a given volume. But electrical gradients can drive this diffusion as well. So here we've got a cell that is negatively charged inside compared to outside. Right? So you could say the inside's negative or the outside's positive. Really all that matters is they're different. Right? The outside's more than the inside. So there's a gradient there, an electrical gradient. If you've got a charged particle, it would tend to diffuse from its like charge size to its opposite charge side. Right? Or in this case, the positive particle would move to where it's less positive or more negative. It means the same thing. How does everybody feel about electrical gradients? Questions about that? Yeah.
Is it similar to when you're doing the experiment with gel electrophysics? Like you have an electrical charge in order to move the color through the to forest gel?
Probably. Are those charged particles you're moving in there?
Yeah.
Yeah, so they're going to go towards their opposite charge.
Well, you physically apply electricity to it, don't you?
Right,
So,
that's
yeah.
fine.
Okay. All right, anything else? All right.
You might be getting to this, but I was just curious of kind of a few examples of molecules that would move this way, because I know it's kind of size dependent.
It is. Where are those examples going to come?
Oh, sorry, I keep reading them.
No, I didn't yet.
Okay.
Think about where that's supposed to come up.
I'll be patient, we'll get to them.
After we get our list of characteristics here, make sure I bring it up, okay?
All right.
Hold me to it.
Thanks.
All right, thank you. So another characteristic. The larger the distance that diffusion is going to occur, the lower the rate of diffusion, the lower the speed. So diffusion works really well over short distances, but once you get out over a longer distance, it's too slow to be practical. Great, what's short and what's long? Well, really, diffusion only works over the distance of about a couple cells, a few cells. You go much beyond a few cells, and it's too slow. Right? So let's imagine, you eat some food, you absorb, I don't know, some sugar molecules right across the wall of your gut. You don't just rely on diffusion to carry those sugar molecules to each end of your body. If you did have to rely on that, you would starve long before those molecules ever got there. Right? So, how do you actually get sugar molecules from your gut to the rest of your body? Blood, that's right. The cardiovascular system pumps it throughout your body. Right? It pumps it throughout, so you don't rely on diffusion. Again, if you're going from, say, one cell to the next cell, or just a few cells over, diffusion works really well. So then, when we went back to that fart in the room, right? So we released that fart, and I said, oh, it diffuses out to everybody else in the room. Well, that was kind of a lie, right? So it wasn't diffusion that actually carried those particles throughout the room. So yes, if we were all absolutely still in here, eventually those particles would diffuse to all the different parts of the room, but it would take a really long time for it to happen, right? But if this smelly compound is released in the center of the room, it's not going to take days for the people on the side to smell it. So how's it actually going to get there?
Convection.
Convection. There's air currents, right, all the way through here. So every time you scratch your head or whatever, you moved your hand, you just created an air current. All these little eddies spin off, and if someone's fart got caught in it, it's spinning off, right? You're never going to look at it the same. But all of this, and even when you laugh, right, ha ha ha, all that air comes out. It pushes the air around and mixes it all up. Right? So there's more to it than just diffusion in that case. All right, let's go ahead and look at this relationship between distance and speed. All right, diffusion distance versus speed. So the rate of diffusion is inversely proportional to the distance squared. That makes perfect sense, right? What in the what? What? All right, let's go ahead and pick this apart. So let's imagine that the distance, we're going to change the distance from a distance of 1 to a distance of 2. We don't care what the units are, but we doubled the distance, let's say. Let's see how that affects or influences the rate of diffusion. So we're going to take that distance, we're going to square it, and put 1 over the top to get the rate. So the initial rate was 1 over 1 squared. What's 1 squared? 1, good job. 1 over 1 is, see how easy the math is in this class? All right, 1 over 2 squared, so remember we doubled the distance. So 2 squared is 4. 1 over 4 is a quarter, right? 0.25. So the rate went from 1 down to a quarter of whatever that original rate was. You doubled the distance, now the rate just went down to a quarter. So it's a lot slower. Okay, it's not a linear relationship. And if we go ahead and graph this out, okay. We graph this out, so we've got on the horizontal axis distance from the origin where we started, and the vertical axis is the rate of diffusion. Right? If the distance is 1 whatever is away, let's say we have a rate of 1. Now you go ahead and double the distance. Now it's 2, the rate just dropped to 1/4 of the original. We lost almost all of that rate. Goes out to 3, it drops down more. And so by the time you get out here, it's almost a rate of 0. And so very quickly that rate drops off. Right? Diffusion works really well close by, but once you get out a ways, it's too slow to be practical. That's what I want you to get away from this, okay? Questions about that? I feel like my voice is echoing off something. Are you guys hearing that?
Yeah.
I'm driving crazy. What is it? Do you know? Only one other person hears it? I don't hear anything. What are you talking about?
I think it's like a natural, like cavernous echo of this room. I don't hear it like echoing off of a specific instrument.
but I've taught here for I don't know how many years, for a decade, and I don't remember hearing it before. Something new. All right, who knows? All right, simple diffusion, talk about passive distance. What else? Temperature. The warmer it is, the faster the rate of diffusion. So why is that? That's right. What drives diffusion in the first place? Well, there's gradients, but it gets its energy from molecular motion. Right? Well, what is temperature? What is heat? It's molecular motion. So the faster it's bouncing around, the faster it spreads out. Temperature goes up, the rate of diffusion goes up. Okay. All right. Size. So whatever this is that's diffusing, the bigger it is, the slower it diffuses. Big clunky things are going to bounce into stuff more often. They're not going to spread out as quickly. A little tiny particle will travel further before it hits something. So it spreads out faster. All right, and lipid solubility. So this one, so 1 through 5 really relates to all forms of diffusion. 6, though, is specifically for simple diffusion. So this starts to get back to, what actually goes by simple diffusion, right? Well, the more lipid soluble something is, the better it gets along with lipids, the higher the rate of diffusion across the cell membrane by simple diffusion. Right? So remember, simple diffusion means it's got to squish between adjacent phospholipids. The better it gets along with lipids, the easier diffusion can occur, simple diffusion. Okay. So remember that cell membrane is made of phospholipids. You've got to get through this section if you're going to pass by simple diffusion. So the more lipid soluble you are, the easier it is to squish through there. All right, I think I've got one more vector system. All right, this is also going across cell membranes. The bigger the membrane surface area, the higher the rate of diffusion. So if you're looking at something diffusing, say, into a cell or out of a cell, it's got to go across the cell membrane. The more cell membrane there is, the more opportunity for diffusion. If it's really small, then everyone's got to wait their turn to get across that cell membrane. But if it's huge, there's lots of opportunity for diffusion, then you can have a higher rate of diffusion. So cells that really rely on a lot of diffusion or a high diffusion rate are going to have a huge surface area. Right? They might have real wavy boundaries like microvilli. Okay? Oh, and then also membrane thickness. So the thicker the membrane, the lower the rate of diffusion. You can think of this, in part, as really just the distance, right? It's got to go further, but also they have more resistance to diffusion. All right, before we go to the next slide, let's talk about what can actually pass by simple diffusion. So, to pass by simple diffusion, one, it has to be lipid soluble. Right, so that's number 6 there. And 2, to get across that cell membrane on its own, it's got to be pretty small. So large molecules like the glucose molecule, it's too big. It's not going to go by simple diffusion. Things that are not lipid soluble, like say a potassium ion, it's charged. It's not lipid soluble. That cannot go by simple diffusion. Water can't go by simple diffusion. Great. What can then? Small nonpolar molecules like oxygen molecules. Right? They can go by simple diffusion. So when you take a nice big breath of air, you fill those air sacs, the alveoli, with air, and there's oxygen in there. That oxygen just diffuses by simple diffusion through the cells that make up those air sacs. Goes right through, no problem. Carbon dioxide can do it also.
So again, simple is must be lipid soluble and small.
Correct. Right. For simple diffusion to occur, the chemical has to be lipid soluble and small. Questions about that? All right, a way to summarize most of this is to look at Fick's law of diffusion. So Fick's law of diffusion really looks at what factors influence the rate of diffusion. It's what we've already talked about. We're just going to reword it. Okay, so Fick's law of diffusion says that the rate of diffusion equals the surface area of this thing that we're diffusing across, like a cell membrane, multiplied by the gradient. Right? So the bigger the surface area and the bigger the gradient, the larger the rate of diffusion, divided by the resistance to diffusion and the thickness. So if there's more resistance or it's thicker, then it's going to slow down the rate of diffusion. Okay, so this sort of incorporates a lot of what we just talked about. There are different ways to think about this. Surface area is directly proportional to the rate of diffusion, so is gradient directly proportional. When one goes up, the other goes up. Resistance to diffusion and the thickness of whatever we're diffusing across, those are inversely proportional to the rate of diffusion. When these go up, the rate goes down. Okay. So what do we mean by resistance? Well, that can involve the size of the particle. So if it's bigger, that's more resistance. Lipid solubility. So if it's not lipid soluble, then there's more resistance. Lipid layer composition. So what is that membrane made of? Right? There could be molecules in there that can reduce the ease of diffusion across it. Does everybody have this written down? Yeah. Okay, how about now? Ready to go? There we go. All right, so this picture just kind of summarizes that. Here's our little cell membrane. Lipid soluble. How easy is it to squish through the cell membrane? Molecular size, the bigger it is, the harder to go through the cell membrane. Bigger surface area, easier for diffusion. Right? What this cell membrane is made of can influence the rate of diffusion, or how thick it is. The gradient, the bigger the gradient, the higher the rate of diffusion. All contributing factors. All right, so we've talked about diffusion in general and specifically simple diffusion. Okay, simple diffusion again just goes right through the cell membrane on its own. That's a passive process. Let's go ahead and talk about facilitated diffusion now, which is also passive. Right? It's a form of diffusion, but whatever's diffusing, it's going to need help to get through. It's carrier mediated. Right? There's some protein in the cell membrane that provides a passageway to get through. So if the chemical is a little bit bigger, like say glucose, or if it's polar, right, like a sodium ion, it's going to have to go by facilitated diffusion, not simple diffusion. It's still passive, it's not going to cost us energy, it just needs a way to get through that cell membrane, a passageway. Okay? We've already seen an example of this, right, with this carrier protein. Right? That's used for facilitated diffusion. Glucose is too big to squish through on its own, but because of this protein, it provides a passageway to get through. It still relies on a concentration gradient in this case. You still need more glucose outside than inside for it to come in, but it needs that passageway through the cell membrane. Okay. All right. With this figure, here we've got a cell with some glucose inside the cell, higher concentration of glucose outside the cell, and here's our little carrier protein. So we've got a gradient. Glucose would love to just diffuse right in. It can't get through the cell membrane on its own, but if that carrier protein is available, that'll allow glucose to diffuse down its gradient from high concentration to low concentration. And it'll keep going until those concentrations are equal. In that case, glucose can go back and forth, but there's no net change in concentrations. Questions about that? All right.
Wait, sorry, what is the difference between the two of them? So high glucose on the outside and then it's equal, okay. Alright.
Got it?
Yeah.
All right, perfect. Anything else? So it could be this carrier proteins, also could be channels like we mentioned earlier. They can also be used for facilitated diffusion. All right, let's talk now about active transport. As the name suggests, it's an active process. It's going to take energy to move things. Well, we're talking about using all these gradients. Where did gradients come from in the first place? We're going to have to invest some energy to make these gradients. Well, this active transport can be part of that. And that will require some carrier proteins to do it. In this case, those carrier proteins are going to use energy stored in molecules like ATP. So if you're trying to move things down a gradient, say from high concentration to low concentration, you're not going to use active transport. There's no point in applying energy to it. Right? It would go on its own if given the opportunity. So active transport is usually used to make the gradients. It's going to move things up the gradient. It's going to push that ball back up the hill so we can let it roll down another time. All right, so this figure here tries to summarize that. Simple diffusion lets chemicals go right through the cell membrane. This thick